Hello everyone, it's April 25th. Actually, I'm not ready yet. I haven't got a pen set up. But anyway, today we're gonna have an easy one, which means, I think finally, no matter what, let's finish that 2576? Is that the one? Yeah, we gotta finish that one. That was too bad. It's been bugging us, I think, for a very, very long time. So let's get that done. All right, let's set it up. This is the note. Okay, good. Okay, so we start with add digit. Should be pretty easy, I guess. Given integer, repeatedly add all its digits until the result has only one digit. Have I done this before? Yeah, I think I had. One digit. Okay, so let's just code it and call it. No, don't now call it a day. We'll code it and get to the other one. All right, add digits. How would you? I think we can say while what? Num. I mean, it's divided by 10, right? Num divided by 10, right? While this, blah, blah, blah. And then eventually we'll return num. And what do we do here? Then we say temp equal to 0, okay? Then we say while num, okay? We can say quotient remainder div mod num and 10, okay? Temp will plus equal to r, and num will equal to q, right? And then we'll go back up and we do div mod again, and when we get out, num will equal to temp. Then we go back up, right? Then we go back up and see if it can divide 10. Okay, we'll run a few test cases. 38 should be 2. 0 shall be 0. That's a good test case. Num. Add digit. Num. Okay, look to be right. We can do throw a few test cases. That's probably too big. Okay. Oh. What do we type? Okay. You try the biggest one. Not biggest one. Like bunch of 9s. Have you tried bunch of 9s? 1, 2, 3, 4, 5. Go. Yeah, looks to be good. Ah, I've done this before. Okay. Nothing much. 2022. $258. Yeah, what's the solution? Digit root while num larger than digit plus equal to this num. Oh, can do that. Yeah, I can do that too. Num equals num divided by 10. Mathematical. What's mathematical? Oh, everyone can be written like this. That is true. Could be represented by a standard way, yes, and everything we can split it up because into 999 plus 199 plus 1, which is this plus 1, which is this times this plus 1, okay? And we split it up. Now it will be this, plus that's the sum, plus 9 times this, okay? And then we take the modulo from both sides. Mod 9, oh, and this is divisible. So this mod 9 equals this mod 9. And you can separate three cases. The sum of digits is 0. The sum of digits is divisible by 9. The sum of digits is not divisible by 9. If what's dr? I think that's the root. So the sum mod 9 is equal to n mod 9, okay? Then if it's big and then it's the sum mod 9 equals n mod 9. So eventually we'll get to a remainder. So you just do a remainder like this. If it's not, that would be this. If it is, if n is equal to 9k, so n is the if n is multiple of 9, right? If n is 0, yeah, that's a trivial case. But if n is multiple of 9, then this will be 0, this will be 0, then we won't know. And because if it's multiple of 9, then we know, right? If integer is a multiple of 9, sum of digits is multiple of 9, right? So if that is a multiple of 9, the sum of digits is also multiple of 9. So eventually we'll go back down to 9. That is correct. Therefore, we'll do this, this, and this. Ooh, that is good. That is good. I bet I used this probably this time. Ah, this is just lazy. This is a lazy solution. Yep. Let's put it. Solution 2. This is from the official solution math approach. If num is 0, right, return 0. Otherwise, we can say remainder is equal to num mod 9. And return this if this, else 9. Will you remember this? I'm not sure. Alright. Let's go and look at the hints. Let's see. Use the LCP array to determine which groups of elements must be equal. Yes, that is correct. Match the smallest letters to the group that contains the smallest unassigned index. Build the LCP matrix of the resulting string, then check if it is equal to the target LCP. Isn't that what we're trying to do? It says use LCP. Yes, we can use the LCP to see which ones are equal. Like say 1, 2, 3 are equal. Right, 2, 3, 4 are equal. Okay, so they're equal. Match the smallest. Well, the smallest will be, those will be A, right? Match the smallest letter to the group that contains the smallest unassigned index. Build LCP matrix of the resulting string and check if it is equal to the target. How long is it going to take if you want to build it? Well, 1,000. Maybe we can find an easier way to build. Hold on. So I think this is pointing to a different direction. Let's see. Is it working? Draw. So I think what it says, can we have an example? Yeah, let's have an example. Let's have the example of I'm actually thinking about union find. Union find is pretty good at doing this. Determine which ones shall be equal. No, there's a 2. Right, and now we already checked diagonal and everything. So basically, let's say that's a 0, 1, 2, 3, 0, 1, 2, 3, right? Then we say LCP 0, 2 equal to 2. Therefore, we can say we can say union, right? Union, because 0, 1, 2, 3, and then 2, 3. So we union 0, 2, right? Union 1, 3. We can do that. And then because this, then we union, then we union. This is going to be 0, 1, 2, 3. No, it's 1, 2, 3, right? 1, 2, 3, and 3. So union 1, 3. Yeah, of course. And then this will union. That's it, right? So based on this, we know 0 equal to 2 and 1 equal to 3, right? So 0 equal to 2, we'll set them to be A. And then 1 equal to 3. And 1 equal to 3, that means they do not equal to 0, right? They do not equal to 0. How do we check that? So we do everything to 0, and then we increment by 1, right? The next one is 1, so this has to be B. Okay, now we build A, B, A, B. Now we need to recreate this matrix to see if it works. How do we recreate this matrix? Well, we already handled this, so we can go row by row. Okay, so the first row we need to compare is A, B, A, B, right? We need to compare this with B, A, B, right? Then we need to compare with A, B. We're going to compare with B. So do we like really compare them? Like, well, we can compare, then this is 0, right? This is good and this is 0. But we have to go through every single one. Right now we go through every single one. And then we go through every single one. Damn, is there a better way to do this comparison, to recreate this thing? I'm not sure. Is there a way to recreate this faster? I mean, if you have compared this, right? This is 0, 1. If you compare to 0, 1, you essentially compare to 1, 2, right? Because you have this compare. If this compare, this compare, and this compare. So you compare 1, 2, you compare 2, 3. Therefore, if you compare 0, 1, you compare to 1, 2, and you compare this. So by this shot, we did a diagonal already. And then you compare like AB, AB with AB, right? So you compare this 0, 2, right? You compare 0, 2, and you compare 1, 3. 0, 2, and 1, 3. You did this, right? So, oh yeah, that's O(n) squared. We can create this O(n) squared, which means every time oh, can you even speak? Every time we create, we will be able to just match. Okay, let's try this. So what I'm saying is we are going to do union find, okay? But we're gonna keep these here. These are just a regular check, but the essence right now is gonna be union find. Oh, dear Lord, class. Wait, what's it called? DSU, right? Yeah. I think we just need a self and n, right? Self dot parent. Parent is gonna be list range n. Okay, and then self dot what? Rank. I think it's 0 times n. Okay, defined int if self dot find x is not equal to self dot parent x, then self dot parent x equal to self dot find self dot parent x, and then we return self dot parent x. I think this is right. We try to find its parent, and if its parent is equal to self dot parent, I'll return. If it's not, then we have to compress the path. All right, union. You can say x and y, right? We union x and y, and this will return a Boolean value. So parent x, parent y, self dot find x, self dot find y, right? And we say if px is not equal to py, blah blah blah, otherwise return false, which means they have already, which then we need to find, right? Then we say what? Then we say if self dot rank, if px's rank is larger than self dot rank py, then self dot parent py, no, parent y, no, parent py, wait, py or y? I think it's py is equal to px. If self dot rank px if it's smaller than self dot rank py, right? So the parent's rank. Then we say self dot parent px. Px's parent shall be py. Else, now they're the same. Then we say self dot parent py equal to px, and self dot rank px plus equal 1. All right, I want to double check. I'm not 100% sure. Useful Bit union fine. Okay. Why did I say XR? It doesn't make any sense. DSU. Ooh, this is not right. Shoot, it's parent. That's the only part, right? So the parent is not equal to this equal to fine. That's right. If it's not equal to, if this parent, else, this equal this. Yep. Almost. We almost got it. We almost got it. But anyway, so that's that. So now we can have, which is union, right? Which is union. Now we just go, for I in range to n, right? And then we say this is actually not necessary at the current moment. Right, and then for j in range I plus 1, right? Oh, I will start from 0. So, but I don't want 0, 0, so plus 1 to n. Okay. And now we say if LCP ij. Actually, we can just say for, right, for k in this. Right, for k in this, what do we do? Well, we say, we need DSU. DSU n, okay? Let's say DSU dot union, right? Union I plus k and then j plus k. So these two are the same because we start from this because they match, right? We move on, so they match. So we'll union them. 4, 4, 4, 3, 4. We get a union, okay? Now we can say res equal to this times n. All right, so we union everything. And then we're going to say for I in range n. Right? And then what we want to find is everybody that with the same parent. Right? Everybody with the same parent. So we probably need to, let me find it first. We say DSU dot find I. Okay, so we find, so we kind of compress. So we will compress the path, and then we will do a, what do we do? We will do a parent and children. What would you call that? Groups. Let's call groups. Okay, from collections, default dict. Okay. Then we call groups equals default dict int, not int, list. Then we say for I p in enumerate DSU dot parent. Okay. Then we say groups. No, it's not. It's just everybody that's the same. We're going to group them together, right? So we say group parent, right? So group parent dot append I. That's what we want. Hold on. Maybe it'll be easier. Maybe we can just start finding. Okay. Wait, but you don't know who they belong to, right? You find the first one, you find its parent, okay? And then you say that parent is going to be A. That's actually not a bad idea. Hold on, we don't have to do this. All we need to do is, so he say P is this, find I, right? And then what? And then what? Yeah, and then what? So what we find is, like, all these must be the same, right? So we fill them out, right? We fill them out, then we set letter equals 97. Okay. Then we can say if res p, if not res p, res p shall equal to char letter, right? And then res I shall equal to char letter as well. Right, then we go to the next one, and then let plus equal 1. We used it, and this shall be res p. Right, and then we go to the next one. Next one we find, I say, if it's already filled, we just use it. If not filled, we use this. Right? Then we just Now we're done. Let's just see if it's correct. Don't do this. Let's try this. Int object is not iterable. Of course it's not iterable. That should be range. AB, exactly. Okay, now we're gonna just say union find to identify which letters, which positions share the same letter, and this is fill the positions that share the same letter with the same fill positions that share the same letter. We go from left to right. And gradually increase. Gradually increase the letter order. Right, so the first we do this, second, yeah. And now last part, recreate LCP and check with the original LCP. So how do we do this? Well, we do this by starting with for I in range n, okay, for j in range I plus 1, right? Because we start with 0, 1, right? 0, 1 in this, and then we can say for k in range, actually we can just say k equals 0, right? And while k plus j is more than n, right? Then we say oh, hold on. You check, and this will count, right? Wait, hold on. We're doing this, right? So we check, and we check, and we check. Oh, we only need to check because we already check. Wait, hold on. Here's the thing. We already checked that they will go this way. So all we need to do is, if it's a 0, yeah, we only need to check the first one. The first one that is a non-zero. That's the only thing we need to check. So we start from 0, right? So I is 0. So we start on 0, 1. Okay? So we check 0, 1, see what this value is, then we compare. Right? And if they're the same, then we're good. And by doing this, we essentially check these one as well, because they will always decrease, right? They'll always decrease. And if it's a 0, then we skip. We check this. Oh, and then we check this. If it's 0, yeah, if it's 0, then we check this. Hold on. How do we handle this? So we say if they're equal, then we check this. We just need to check the last one that are equal, which means I shall go from this position, from the bottom, check up. Right, from the bottom, check up. From the bottom, check up. Okay, so what you're gonna do? So I have 0, 1, 2, 3, right? 0, 1, 2, 3, and 1, 2, 3. So we check this, and then we check this, and then we check this. This. Okay, so I changed the strategy. And in fact, I like the original check. I actually don't like this. We still need some symmetry, and then I guess it's fine. Yeah, let's just do this, and the check will change. How it change? So n, the j, okay, we always go from n minus 1. Okay, j will always go from n minus 1. Upward to n minus 1 to I, but we don't reach I, n minus 1, right? And then this is I equals 0, so it will be 3. So we check 0, 3. You're saying we check 0, 3? No, we don't check 0, 3. We check. Dear Lord. We check this. How do you express this thing? This is 2, 3, right? 2, 3. So this diagonal, So I shall start from the difference between the two, or the size. Okay, maybe I should do this way. Right, for k in range 1. Okay, so because I and j, the difference is 1. All the way to I and j, the difference is going to be n. Right, because this I is 0, j is 3, right? And that's it. So that's that. And then we say for I in range. So I want to go from bottom up. This, right? And then this. So I shall go from n minus k, right? N minus k. Oh, this is actually n minus 1, n minus k minus 1. That's first I will go, right? All the way to 0. That's what I goes, right? And j shall equal to I plus k, right? I plus k. And then what do we say? Well, we accumulate, so we say ACC shall be 0, right? And then we say ACC plus equal to res I equal to res j. Yeah, we're into this, right? If they're equal, let's see. And then we say if ACC is not equal to LCP IJ, right? Then we shall return this. Boom. Terrible. Otherwise, we go back. So I move up. Okay. I move up. And J is going to be this. Then we check again. Right? Because ACC will increment. Okay. So we go with everything. Now, when you put it that way, right? When you put it that way, we could like not do this, right? We could check, just do this, right? If we check do this, then that's everything. We're gonna start with the same, right? And then we check. If it's good, then we'll return dot join res. And with that, we don't have to do this anymore. Joint. What are you thinking, man? You want to smoke something? Index out of range. 0, 1, 2 is good. 3 is bad. 3 is bad. Oh, symmetry. It's bad because of symmetry. Damn. I guess we have to check symmetry then. Check symmetry then. Because the rest can check. Right? You know what? I think this check is still needed. I think these checks still needed. And make sure it works, and then we'll check this. I mean, in that case, we already checked, so we can go from 1 to n. It's fine, doesn't really matter. Check symmetry, diagonal, right? And max possible value. Yeah, I think it's max possible value. That one tripped us up. All right. Oh God. Oh, I thought we got it. thought we got it. Oh, jeez, man. A, B, C, B, B, A, B. Alright, so it's the check has issues. Alright, why? Why does the check have issues? Hold on, let me think. I is at the bottom. J is I plus 1. Okay. So we start. K equal to 1. J I equal to this, K equal to 1, so we are in this position, right? The last. Wait, hold a second. Hold a second. What is a start? We start with this position, right? I equals 2. J equals 3. So we take 2, 3 compared to 3. Right? And say if they are not the same, there shall be 0. And then we say that's ij. Yeah, and then I goes up. I become 1. J become 2. Right? I become 1. So 1, 2, 3. J become 2. And I'm comparing J's 2. I'm comparing these two, right? And if they are the same, then ACC or plus equal to. And then, whew, eesh. What's the problem? This is absolutely correct. Okay. I need, oh my god. I hate this. I hate this so much. Where did I miss? So temp ij equals ACC. Okay, then maybe we can print temp. I think that's not a good idea for row and temp. Print row. Okay, and then we will say for row in LCP, print row, right? And then we'll print like something between. Ooh, dude, that diagram looks so bad. Holy crap. I mean, of course, it doesn't matter. The diagonal, it doesn't matter. What matters is that's a 0. 0, 1. Oh, 0, 1, 0. 0, 1, 1. Ew, that's ugly. I know why. Holy crap. So we shall say if res I is not equal to res j, ACC need to reset. Else, so basically ACC shall equal to 0 if this. Else ACC plus 1. It shall be this. There we go. There we go. A little bit error here. Yeah, because in the reset, whenever it's 0, you have to reset. You forgot to reset. Try the others. Yeah, sure. Oh, I think this one holds. This one holds promise. Lots of promise. And honestly, it's not that complicated if you think about it. If we use another, is this part of the test? Yeah, it's part of the test. All right, let's just go for it. Oh no, come on. Oh, come. Oh. My bad. My bad. My bad. Did not consider this. Okay, okay. I admit defeat on this one. Which means at any point it's 27. That's gonna be bad. Well, no. It's just we have to check here. We start with A, and letter cannot be larger than 122, right? We had 26. Right, 26 is 123. But 122. 122 minus 97 is 25. Plus 1, yeah, cannot be larger than. So this plus equal 2, and then when we do this, right, if not, then we're going to say if letter is larger than 122, then I shall return this as impossible case, because we go beyond Z. Okay, so that's that. Even with the hint, right? I still have issues. I don't know, it goes so slow to make me feel like worried again. Oh my god. Time limit. Time limit? What? What are you talking about? What are you talking about? Oh my goodness. Which one? I mean, union find is pretty fast. I really don't think it's the union find though. Oh, God. Okay. How long does it take to run this? No, yeah, it does take a long time. Okay, so we can say what if we comment out this whole thing? What if we comment out this whole thing? And then union find for k in this, right? Then we can say if I, now j is larger than I, so if j plus k, right, if j plus k is larger or equal to n, then we'll return this. Otherwise, we're union. So that's take O(n) squared. O(n) squared times k. Ooh, maybe that's the reason. This is O(n) squared times k. And this is O(n) times the find, which should be nothing. This is O(n) squared. So this takes the longest. Let's try. Whatever it is. I mean, try it here. So what I'm saying is we're gonna comment out all this. Okay, this might just take too long, and we will do this extra check because that's an impossible case. Okay, and we will run this and then see. Ugh. What are these? It does not. Oh, of course, we have to go start from n. Oh, but still, we still have to check diagonal. We can check it here, right? If this is not equal to and ACC is not equal to LCP, JI, right? JI. If that. What? Or. Okay, or. There we go. Okay, let's try this test case. Oh my god, how big is this test case? Holy crap. Don't even know. You don't even know it's... Shoot, I don't even know it's... Hold on. We will reset this whole thing. Let's copy and paste the solution. Okay, and run the code. That's not it. That's not it. So this means we need to be faster. Faster to, oh my god. So this is the problem, right? Yeah, if you think about it, we should not do it this way. We probably should do it this way, right? You go diagonal. Yeah, we should do exactly the same way here. I have no clue why you did not think about this. We shall do it this way. Do it this way, right? Then we don't need ACC, right? We go, I mean, we can go from 1 to n, right? We can go from 1 to n. And then we go I is this, and then we say j is this, and then we say if, right, if LCP, LCPIJ, wait, hold on, this one is not ready yet. If LCPIJ, right, if LCPIJ, which means these two match, then we'll do union. This made me think. And then how do we check? We need to check the size, right? It cannot be too big. Well, but it's okay. The check can be done here. So we say, oh, we remove all of this. If this, right? Then these two must match. Is that right? We go from diagonal. With diagonal, go this, right? If it's larger than 0, that means they must match. We go back up, and if it's larger than 0, that means they must match. And if it's equal to 0, that means they do not match. And we just do diagonal, and then we do this, and then we do this. Let's see. Oh. Oh? What? That's interesting. That is very interesting, to say the least. Index out of range. How? K from 1 to n, right? I will not go out of range. And then j equals I plus k. So I plus k, right, is just whatever I value is plus k. So the largest is n minus 1. And if this is fine, how come this is not fine? Oh, I see. I find j already. So I can do this, which I think maybe we just don't need j. Maybe we do this, right? And this is just going to be I plus k. And this I need j because j is used a lot. But here, j only used once. That is not cool. That is not cool, man. We passed the last, but we failed this one. Okay. That is fine. Let's check. Let us check. Printers. What do we get? A, B, B, C. Oh, we have a D. A, B, B, C, D, C, B, B, A, B, B. That is very interesting. That is very interesting, to say the least. Let me think. So we go from this, right? And then basically this is saying, this is one thing, is saying it's not matching with others. Huh. It's not matching with the others. LCPI and I plus K, right? If it's a 0, because we go bottom right to top left. So if we find a 0, that just means these two do not match, right? So this do not match. Boom, this one we match. So we will match them, right? So we do this. So they do not match. They match. So a union these two. And then they match. How would this not match? I don't understand, man. I do not understand. Okay, let's print DSU dot parent. Zero, 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4, 5, 6. Wait, hold on. 0, 1, 2, 3, 4, 5, 6. Huh? 0, 1, 2, 3, 4, 5, 6. 7, 8, 9, 10, 11. Wait, what? 11. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 is A. Dude. Find 0, 1, 0, 1, 2, 3, 4, 5, 6. Find 6. What does we have? Find 6 is 10. Find 11 is 10. What? That doesn't make any sense. That does not make any sense, man. It does not make any sense. Yeah, final 11. Wait, hold on. Find 10. Find 10 is 1. Why would it... Oh my god. I have nothing to say. Stupid is as stupid does. Sometimes this is how I am. Sometimes this is how I am. There's no excuse. No excuse at all. Okay, this shall be right. Because it is just... Right, we go union find. We go union find and we go this. And then we run this, that shall pass. Come on. Come on. Give me some. Give me some. Let's do this. Okay. I think we got it. Well, it's still gonna take a long time. Oh, Jesus. Alright, we're not gonna use this test case. Okay, let's submit this. Like two tricks to handle this. Oh, finally. Finally. We start with 19, April 19th. I even took a trip and then I get back. And we did a weekend. And then finally on 25th, we got this. And honestly, it's not that complicated, right? It's not that complicated. The hint helps. Well, the hint helps a lot. It points to the direction of union find. We first use union find to identify which positions share the same letter. Then we can recreate. Then we can create the string, right? From left to right, filling all the positions, right? For all the positions that share the same letter, the smallest letter available at the moment. Then we recreate LCP. Well, not literally. We recreate the value at each position of LCP and compare it, right? And compare it with the corresponding value in LCP to check, right, whether LCP has it right. Now there are two tricks, right? Three tricks. Oof. One, the LCP matrix needs to be traversed diagonally from bottom right to top left, because this way we can obtain all the information either for union find or for recreating LCP in O(n) squared time. Otherwise, if we traverse it row by row, it will take O(n) triple time. 2, when filling the letter, make sure to check whether the letter has exceeded the lowercase English letters. Number 3, when checking LCP, make sure to also check whether the mirrored position has the same value as the required. Now, whether the target cell, right, in LCP and its mirrored cell share the same value as desired. Okay, so I call this O(n) squared times union find, whatever union find is. Time is pretty bad. Okay, what do people say? Yep. Union find. What the hell is a z function? There's no union find, huh? Okay, what'd you say? Yeah, let's do this tomorrow. The learning never stops. I probably will go through a couple. This is this is nightmare. You think this is a nightmare? No. Save this. Yeah, for sure this is a nightmare. Come on. We'll add to the list. This is a nightmare. I mean, yeah, it's hard to say. We did solve it, but it took so long. Part of it is sometimes I just got lazy. I just don't want to do it. Anyway, nightmare is nightmare. Alright, that'll be it. I will see you guys tomorrow then. Adios.